Yeah, I did. Yeah, algebra equals fun. Woo! Okay. I say that because there will be some algebra today. Hopefully nothing that looks completely unfamiliar. You're like, what's going on? But there will be a little bit of it today. What we're going to do today is we're going to take some rational functions and analyze their graphs and do a little bit more study as to what their graphs tell us about certain situations. All of this hopefully should feel familiar to you. You have done the math part of it, the algebra part of it before. And you should know enough to hopefully have this be a very intuitive experience. So let's get started. So people need drugs to stay alive. People also take drugs to die, which is bad. But the good drugs that people take help them live. And people like doctors and pharmacists and people like that give people drugs at certain dosages and certain concentrations to make sure they stay alive and healthy as long as they can and to experience less discomfort than what their illness is trying to give them, things like that. So when a doctor prescribes medication, he has to know, or the person who made the medication at least, has to be able to tell the doctor how long that drug is going to stay in that person's bloodstream and what concentration of that drug needs to stay in the bloodstream so that the patient is able to feel relieved from their symptoms or to experience a cure in some way, whatever. You get the idea? Like they have to have enough drugs in their bloodstream in order for things to work properly. So there's lots of functions that model that, a lot of exponential functions that model that especially. But here's a rational function that also models a similar behavior for a special type of drug. So C of t equals this mess here, where t is the number of hours it's been since the drug was taken, and C is the concentration of the drug. And they use this this unit here, milligrams per deciliter, okay, of a certain medication, and it's taken orally. So we're going to graph the function for a reasonable domain and try to just interpret what the graph shows us. So let's graph it. It was 40t, so 40x over, make sure you put the denominator in brackets, 1.1 x squared plus 0.3 and bracket. And what's a reasonable domain for this thing?
My calculator is x max 131.
131?
Yeah.
That's a long time. 131 hours? I don't know if it would go that long. Maybe. What do you got? Yeah, okay. What? No, that's your Y max. Okay. Yeah, that I could believe.
X is
10. X and 10 and 10?
Yeah.
Okay. Since it's a time unit though, I'm going to make the X minimum just like -1 so I can see the axis still. And then Y min, we'll keep it at -5. Y max, we'll make about 140. Okay, let's see how that looks. Oh, too tall. Maybe let's go 75. That's a little better. That's interesting. There's a little peak. Why is there a little peak? Yeah, you take a pill, it doesn't instantly get into your bloodstream, does it? It's got to dissolve, right? Go through your digestive system, get absorbed into your body. So the concentration initially is increasing, right? And then once it's peaked, it'll peter off as your body flushes it out. Right? How long does it take for the drug to take effect would be the maximum at that point, right? So we can find that just really quick here.
So you never get the drug out of your system completely?
Yeah, that's a good question. Mathematically, no, you don't. Realistically, you probably get rid of it. Like the Tylenol you took when you were 2 for your toothache is probably not there anymore. Mathematically, it's there. Still got Tylenol running through your body. Right? But it takes about half an hour for the drug to fully be in your system, and then after that, it'll peter out. Does that make sense? What's your problem? Now it makes sense? Oh, okay.
Are you tracing for the peak or?
I just did a maximum amount, second calc, and then max. Found the max. Good? Okay, so let's go back here. So, doctor needs to know when a patient's bloodstream drops below 10 milligrams per deciliter. That would be when he would or she would need to take more pills to keep the dosage up. What time does this occur? Right, that's just a nice algebra problem. Okay, yes, algebra, even though we could do it with a graph. So we make C equal to 10. That's the concentration, the target concentration. We want to know what time that occurs at. Equals 40t over 1.1 t squared plus 0.3. Right? And then we just crash through the algebra. And like I've said before, you should know how this works. What would be the next algebraic step in this if I was solving for t? Got a fraction on either side. Cross multiply, right? So we're going to cross multiply. So we get 10 times that mess. And 40t times 1 is just 40t on the other side. So this gives 11t squared plus 3 plus 3 equals 40t. And bringing everything to one side. Got a nice quadratic equation. Could do magic number, right? Is it feasible to? It's 33. No, I'm going to do quadratic formula. So 40 plus or minus negative 40 squared minus 4 times 11 times 3 all over 2 times 11. You guys following me? I know I'm going a little quick, but this step here we could have done magic number factoring, but a little tough because factors of 33 that add to equal negative 40. It's a little tough, right? So it's probably going to be a decimal number. So we use quadratic formula. Good enough? Okay. So this is, what would this be? 40 squared is 1600. And then 44 times 3 is 132. All over 22. And then from there, we go 1600 minus 132 is 1468. All over 22. And the square root of 1468, what is that? It is 38.31 all over 22. And now we get the two values for t. So t is either 40 plus that value divided by 22 is about 3.56. Well, 40 minus that value is about 0.07 seconds. Okay, so basically what's happening is when the patient first takes the pill or the drug, the concentration hits 10 milligrams per deciliter pretty quick because it starts from 0 and spikes up pretty quickly. It doesn't stay there for very long because it goes above that quite fast. But about 3.5 hours later, sorry, they should say hours, 3.5 hours later, the concentration hits 10 milligrams per deciliter again. So by that time, the patient is going to need to take another pill. And basically that's like every meal, right? There's like 4 hours approximately between each meal, and so the patient would need to take a pill every meal. And so they would communicate that, or the pharmacist or the person creating this drug would communicate that to the doctor, and they would share that information with the patient. All right?